I hope it's okay now. And it's a great pleasure to come back to give a talk, and especially for Jim. It's for various reasons. So, so what I'm going to talk today is some work I did in last year, continuing until now. So it's a problem I was interested for a long time, but it really got started by a paper of Simon Donaldson and Richard Thomas. And so it's getting real progress when I was visiting ETH last spring. So since then I tried to write down what I got, and it seems to be things always improve a bit. So it's until now I almost done. Okay. And so during this course I benefit a lot from conversation with a lot of my friends, like Jeff or East and Toby. Okay, so what I'm going to talk today is to show you. I guess I even title change a bit. So in this talk, I will show you a connection between Yang-Mills equations and the classical minimum surface, which a lot of people probably see it in the classical differential geometry. So this work, there are not parts, many parts of this work you can go back to a work of Jim Simon. So I think this is probably a appropriate topic to talk today. So in the end, so let me see. So as we all know, there are many interactions between very intimate, very close relations between a series of functions, or more generally vector bundles, and a series of submanifolds. So the typical example you can probably, if you are algebraic geometry, you can think is on any algebraic surface, the group of divisors is the same as the group of the Picard group, which is somehow is group of Miramov functions. So it's in many problems it's very interesting, or it's of fundamental importance to find out how those things are related. So today I will show you an example. You can think this example, one more example. So you can think this example extends some previous work, say at least, which I probably say later. So basic philosophy here is what I try to say is actually the minimum surface is nothing more. It's just the basic Yang-Mills. So it's just a limiting case of Yang-Mills, which I'm going to show you. Okay, I show you how this can be seen. So since this is the last talk, I have to apologize to give you some very simple things. So it's actually after hearing so many good talks, and particularly a lot of talks, and already give some of these backgrounds for this, at least analytical backgrounds for this work. So I probably feel a little bit easier to do it now. But nevertheless, I show you something trivial. So let me start with Yang-Mills. Remind you what the Yang-Mills function is. So I start with a manifold M. It's equal to, if you like, just take this as a domain in the Euclidean space. And so we start with a vector bundle over there. It could be trivial. So usually we require this vector bundle has a structure, a particular structure, say this structure group G. So in this talk, you can just think the G is a unitary group, say like SUR, any SUR. It's okay. And what's wrong? So the connection is A is just given by a coherent derivative of from sections, space of section to one forms with values in the E. So locally is essentially given by one form, and as already written down in the modeling, the curvature is of this form. Okay. So it measures the commutator of second derivative. Okay. So anyway, so Yang-Mills functional is defined this way. So it's an integral of L to norm of curvature. And if you check a Lagrangian equation of this, with a Lagrangian equation of this, you will get a divergence-free equation. So this dA here is nothing else but just dA star is just the adjoint operator of dA. And the second equation is always true. It doesn't matter for what connection you are working on. So it's just second Bianchi identity, as we all know. And from here, if you if you remember what Bland talked in the morning, in the first talk in the morning, you will probably see even for some manifold we have a similar feature here. So in place of a second Bianchi, you have actual Kodály equation on the second fundamental form, and the minimality, which it says mean curvature is 0, is just it's analogous to that first equation over there. Okay. So probably this is I don't know who literature whether it's explicitly written down or not, but when you work on this more and more, you realize that's actually what you are leading to. So this I should say like Professor Yang said in the morning. So somehow the gauge group, once you know there's a gauge group action, you probably think this is something you do it in private. Okay, so let's say so I just remind you this equation in general, unlike minimal surface equation, it's not elliptic system. So the reason is because there's a gauge group action. So the gauge group is locally is just given by maps from a manifold into group. Okay, the group we are talking about. So as I said, in this case, you can simply take a group to be a unitary group. And the method, as you will I hope you realize in the end, is can apply to more general cases, like the case with Higgs field or so on. Okay, so the equation is invariant under this. So we back to in order to find some reasonable geometric things, we always try to take a quotient or always modular group action. Okay, so what I like is, of course, this equation has to be studied extensively, as you already seen from a few talks in the morning. So what I'm what I'm interested in is a special solution of this. Though you can try to do in a very general case as an analytical problem, which I may do it. We come back later. May do it later, not today. Okay. So I'm particularly interested in some special solutions of certain type. So maybe first one is very trivial. I just try to say if you look at the abelian case, say the group is U1, then what you are doing is just say FA is the harmonic form. So which goes back to something which you will know all the time in the Cauchy theory. But in fact, in the last few months, let's see. So this connection thing somehow is trying to generalize things to a harmonic theory to this non-commutative case. So actually, in the last few months, and for example, East always asked me whether or not there's a version of similar things for P fields, for P harmonic forms, which I don't know at the moment. Okay. But anyway, so this is a natural extension of standard harmonic things to a non-abelian case. So among those things, let me look at the particular solution, which are minimizers of the Yang-Mills equations. And so now I will, in order to do such a things, let me give you assume there's actual structure on manifold. So this means I have a differential form, closed differential form, omega, which is of a degree n-4. So with this form, we can consider the following equation. The equation means if I wedge the curvature by omega, I get n-2 form. So then I take a Hodge operator. Start here is a Hodge operator. I go back to the 2 form. So this way you can define actually symmetric product on a symmetric operator on the 2 forms. And so then you ask whether or not when you apply this map, you get the vector curvature itself. So if it is, I say this is the anti-self-dual solution. So the proof of this is probably you can think it's very easy. I think I wrote somewhere, I couldn't find it now. So basically, you have a Bianchi identity here. Then this is 0. Then the divergence equation, you simply apply to divergence equation. Then because you have a star operator there, so it goes back to the Bianchi identity again. So the omega closed is just used there. Okay. So that's why I say you always get this solution. So what's good about this is when you try to do things, I will tell you a few motivations a little bit later. So the solutions I discussed here has a very nice property. For example, if M is compact, then omega, if A is omega anti-self-dual or just anti-self-dual, then you automatically bounce the curvature here. Okay, so at least in the L2 sense. So in the L2 sense, the curvature is just given by a topological quantity. Okay. So that's very important when you in the application because then you have a compactness. So I give you a few examples. In fact, I should say this equation was already written somehow by physicists in the different forms. I think this is a convenient way of writing down all known self-dual type solutions. Okay, it's very simple. So for example, you look at n equal to 4. So what you can have is omega equal to 1, right? So in this case, just anti-self-dual standard anti-self-dual solutions we have seen a lot in the Donaldson theory. So then we go back to let's go to another case. We are probably I go a little bit fast now. so another case which we know all the time, at least since I was a student in the 86. If I take M to be a Kähler manifold and omega to be a Kähler form of G. So G is a metric I probably forgot to say at the beginning. So I fix the metric for all the time. So suppose omega is a Kähler form. So then the n over 2 is a complex dimension of a manifold. So let me just use this form. Okay. So use this particular form. So then what the anti-self-duality tells you is something we know before. So this is so-called Hermitian-Young-Mills. Because what is Hermitian-Young-Mills? That is the following. So if you just think it's on the Cn, say kept locally just on the Cn. So you know you have since it is a complex manifold now, so you can decompose your 2 forms into 3 types. So one is a 2-0 type, and one is 1-1 type, and 2-0-2 types. So now you write your curvature into different types like F20 and F11 and F01. So the Hermitian-Young-Mills simply means the F02 part of that is 0. And the same is equivalent is the F20 is 0 because of a unitary property of connection. So then the F11 part, which has a trace 0. Okay. So this is called Hermitian-Young-Mills, and by the well-known result of Donaldson, Yao, and Uhlenbeck, I guess Uhlenbeck and Yao, I think, so in the right order. In 86, those connections are in the one-to-one correspondence with so-called stable holomorphic bundles on the manifold. So also we see from here, these anti-self-dual equations in general is not elliptic. It has more equations than variables. because so this gives you a perfect example because holomorphic condition is a overdetermined system in general. Okay, so that's why I want to give you one more example. This is in the work of Donaldson and Thomas. So this is so-called complex anti-Ceph2. Okay. So I take omega to be a Kähler form again. So this time assume M is the Calabi-Yau 4-4. So for example, like complex 4 tori, complex dimensional 4 tori. So Calabi-Yau, for Calabi-Yau 4-4, you have actual structure, which given by a holomorphic 4-0 form. So let me normalize this so that you have that identity over here. So now I take these particular things. Okay. I take this particular thing, particular form. So then the things, the omega anti-Ceph2 will give you a so-called complex anti-Ceph duality equation. Was discussed before by those people. So more precisely, the equation is given like this. The 1-1 part is still same as before. So we are still working on the Kähler manifold. So however, the F02, the 0,2 part of curvature is not completely 0. It's only half of that is 0. So this F star theta here is like complex Hauge operator. So just remember, in the 4-dimensional case, once we have a metric or have a volume form, we can define the Hauge operator for two forms. So in this case, with volume form replaced by this holomorphic volume form, you can define this complex Hauge operator. Okay. So in the exactly same way, okay, which I hope you all, I think you all know. Okay. So this turns out is actually an elliptic system. So what's actually I feel more interested because this is an elliptic system, and it's actually also related to a previous case, namely if A is complex anti-Ceph2, whether or not it actually gives you a holomorphic structure, it's determined uniquely by topological structure here. Okay. So this is very nice. This actually gives you a more stabilized version of things, because holomorphic structure are not very stable because you perturb a bit, it's gone. Okay. So this elliptic system gives you some hope in say improving in trying to find holomorphic cycles in the most invariant way. Okay. Okay. So of course you can also later on will say there's another similar condition corresponds to a Lagrangian case, which has also some interest. So you can find more examples of this type. In fact, a lot of these particular solutions of this Ceph2 equation was already discovered by physicists, and so I give you some. I don't want to go on because it's just give you some just a briefing, just brief a bit. Okay. So if you can, for example, in the first case, it's actually a more general version of the previous case. So it consists being 7 manifold or G2 manifold. You have omega. You just take omega to be that standard form, which give you that special structure. And if you, I don't want to go on. So if you are more interested, I think I recommend you to read a paper by Reese Harvey and Lawson. So all these forms, or at least was written there. Okay. So these equations and previous was discussed by Donaldson, Thomas, and also by Boileau and Canon and Singer, okay, and so on. In fact, you can write more particular solutions and for special manifolds. It very much depends on representation of holonomic groups on the cotangent bundle. Okay. So let me say. So I give you at least give you enough examples of these things. So all these anti-Ceph2 equations or solution of this anti-Ceph2 equation could be thought as as a calibrated case in the young males, which I will show you now. So before I show you, maybe I say a few words. So what I want to do today is I try to consider some model space, which we all it's quite popular in the last few decades. So I consider solutions of omega anti-self-dual equations of fixed bundle E. Okay, so I model the gauge group, always model gauge group. So I fix omega and E. So I hope to define, the general motivation here, I try to define some invariants of M, which are deformation type, deformation invariants, by using this moduli space. So we already saw a lot of cases like that, like donuts and polynomials, and GW and the Gromov-Witten invariants and Seiberg-Witten invariants in the past. So in order to do this, there are a few problems a few difficulties you want to overcome. So the first, you want this at least to be non-trivial. So at least there's a hope to being non-trivial. So that's the first thing I already mentioned before. So the equation you are talking about should be elliptic. Otherwise, I said over-determine the case, you perturb a bit, everything is gone. So okay. So second, which is the main topic today, I try to compactify it, okay, so that you can really count the number of points. So last one is I want to say, so when the omega E are in the general position, you want this has a nice structures, which is invariant and perturbations, so that especially kind of transversality property, which I haven't done yet. Okay, if you So of course, you can also talk about if you want to define over integers, you want to have orientation and so on. Okay. So ellipticity is very easy because, as I said, you can define the operator. So which I already mentioned. So which is defined by this equation over here. It's easy to check. It's symmetric. So it has eigenvalues. So ellipticity basically says is same as saying the rank of this is n minus 1. So why is n minus 1? Because the connection is given by n variables. Let's just look at the abelian case. Okay. Then you have a gauge transformation, which counts one-dimensional. So what you left, the freedom you left is just n minus 1 dimensional. So then you don't expect the constraint to be more than that in order to be elliptic. So that's why this condition is put here. So you can check, go back to the case, this of course this case is trivial, and also this condition is satisfied for complex anti-self-dual equation on the Calabi-Yau fourfolds, and it's true also on the spin 7 and the G2 and so on. Okay. Okay, so this is for a simple remark on the ellipticity. So that's why I, instead of considering this holomorphic connection, which has F020, we try to consider some more general version of that. So I try to compactify it. So this is where we will see the minimum surface. So the complication was there are a lot of compactness theorems. So particularly I just mentioned the case which is very close to my work here is when n equal to 4, the complication was constructed by using a compactness result of Karen-Uhlenbeck. So in that case, as we will see, the things you add on, in that case, supposed to be points. So the geometry structure of that is, there's no more geometry to say about points, I guess, at least in our case. Okay. So So I will construct a complication of this by attaching a special cycles in any dimensions. Okay. So now these special cycles mean by special cycles I mean those subsets which are closure of because in general even in holomorphic case you might have subarray, you may have a singularity. For example, for curves you may have isolated singularity. So I have to include that. So what I say here is I want some subvarieties which are calibrated by omega. So subvarieties always there's a big part which actually as open part which is submanifold. So on the submanifold you can talk about the calibration which was discussed before in a general form by Harvey-Lawson. And so that means I want to restrict the omega restrict the volume form on each tangent space. And there's a slight difference here from probably from things discussed in the paper of Harvey and Lawson, because here it's even its calibrated is not necessarily minimum yet, because in general there's actual condition in order to assure the minimality. Namely, you want this omega has a so-called conormal to be 1. That means if you restrict this to any tangent space of proper dimension, it's less equal to volume form. Okay. But anyway, so in these things I discussed here, I don't need particular I don't need that condition for at least to see to get compactness. And if that condition is satisfied, of course its structure tends to be nicer. Okay. Okay. So I give you some examples. Of course, these special cycles already used, say even say Gromov-Vitti invariants, you count the holomorphic curves. So which from the things I'm going to see later on is somehow related to rank 2 bundles. Okay. So also it's there's some recent interest in the special cycles which are not holomorphic type in the string theory, due to a paper of Stroming, Yao, and Zaslov, which predicts the existence of foliation by special Lagrangian for Calabi-Yau 3-fold or 4-fold or whatever for Calabi-Yau. So the simple example of this is corresponding to 2 cases I discussed for connections, for Yang-Mills connections. I first talk about Keller case. So in this case, you choose the same form I used before, but this time the omega calibrated cycles are just holomorphic subvarieties. It's an easy exercise to check. Okay. So for example, for m equal to 3, say like a 3-fold case, you get holomorphic curves. Okay. So holomorphic curve may have isolated singularity anyway. So the second case I want to bring your attention is corresponding to a previous third case. Is when m is Calabi-Yau's 4-fold. So I have this actual structure. I use the same omega form. Okay. So you will ask what the corresponding cycles are. So those cycles I call the Kelly cycles. You just take this as definition. The Kelly cycles are omega calibrated. So following a Harvey-Lawson. Okay. There's some equivalent way of describing this. So in those cases, has some particular interest because they include a special Lagrangian submanifolds. So in general, the existence of special Lagrangian manifolds is very elusive to us because we don't have unlike holomorphic functions. So we unlike holomorphic submanifolds, we in general we don't have some nice local theory to describe. To describe this in corresponding to functions. Okay. So maybe I should say just write down forwards here. So there are two things. Right. And corresponding to this fact, I maybe point out in a moment. Okay, I guess I couldn't find my pen. So one case corresponds to if you may ask the following thing. Let's I remind you this thing here. So remind you the corresponding statement for holomorphic. Sorry, it's not this. Now ask you this fact I said before. If A is a complex anti-self-dual, then this is corresponds to holomorphic thing if and only if this is a 2-2 type. And this thing is also true for this case, which in a form like this. So you can state not. Okay, so which you can say a Kenny cycle I guess not quite. So it's a holomorphic cycle if you have this condition. So if it's a Poincare dual of this cycle is a 2-2 type. Okay, and it's a special Lagrangian if it's a 4-0 type. So you do have also similar homological condition to characterize the holomorphic one from a general Kelly ones. Okay. So there are, from here you might, as I said a few, and I said more. I think, or I also mentioned at the beginning of beginning of this talk, there are a lot of correspondence between the minimum surface in general and the Young-Mills. So for example, look at the Bianchi identity and the Cordasi equation. So now let me to discuss something again more, which is involved in a proof. So if I consider A is a connection, so if I look at this volume form over here, so I can consider this the dimension of this volume form, which actually behaves like volume form n-4. So why? Because you just look at the scaling property. So scaling property, if you change your scale of a metric in that way, then this measure over here, d mu, behaves like this. So this is true also for volume form of n-4, of dimension n-4. So if you believe everything discussed here are very much like if you believe this is the real electric extension of the minimum surface of n-4, so then you expect the following. Because if A is the Young-Mills, then you expect the monotonicity, which was known for minimum surface for long time before it was known for Young-Mills. So this was things proved by Price in '83, which he proved. If you look at the normalized version of this, normalized form of L2 curvature, then it is monotonic increase as R grows. Okay. So then from here you can prove Epinal regularity theorem as as Jeff said before. So that's somehow a typical thing you want to do in analysis. Okay. So namely, you can prove if epsilon is, there's epsilon and which is small enough, such that for any r which is fixed, such that this normalized measure is less equal to less than epsilon. So then you expect this is then the curvature is almost flat in the sense. So this you can forget about this. You can think r is 1 after scaling. Okay, this quantity here is a scaling invariant now, okay, because that and the property I wrote on the top. So then you expect things like that. So of course these things, similar thing was known for minimum surface. So if you replace f by second fundamental form, that basically says that once these things is satisfied, then you have near that point the surface is rather flat. Okay, so which is measured by second fundamental form. So this was a result of Uhlenbeck and also observed by Nakajima. I also read in the preprint of Nakajima. Okay. So let me say one thing here, because improving these things, it's now it goes to this Jing-Simons identity. In fact, if you think curvature as a second fundamental form, so improving this, you need to derive the elliptic equation on the curvature, which is has a similar feature like Jing-Simons identity. Okay. So you can see a lot of these examples in this. So okay. So once we have this, so what we conclude, what Karen conclude is the following. So you can conclude the following: some compactness result. Maybe I didn't state in the best form. Okay. So you don't want to see a sequence anyway. So I let me state in the elementary form. So for any, so that the corollary of that is the following: if for any sequence of connections in the moduli space, and there is a subsequence and a closed subset which depends on this subsequence, such that this sequence converge to the limiting connection, which is also Yang-Mills, because Yang-Mills, if whenever this is smooth convergence, this Yang-Mills property will be carried over, right? So that's easy to see, and modular gauge transformation, which we always do it behind the thing. Okay, this will cause some actual difficulties actually. So and moreover, this S, which I forgot to say here, this S, actually dimension of this S is less equal to n minus 4. So dimension here, if you don't know any regularity of S yet, the dimension is referred as the Hausdorff dimension. And not only dimension is less than equal to n minus 4, and the total measure of total area of this set for this dimension is actually finite. Okay. So you can roughly think this can be can be somehow intuitively believed. So in fact we can categorize S. So the S is just where the curvature is not the curvatures of this connection or sequence of connecting do not uniformly die out and flat out and near the at along the points of this S. Okay, so that's what this mathematically what this condition means. So So if you think, sorry, here I assume this AI. Let me just identify AI with AIJ. It doesn't. It's still a sequence. Okay. So then you think this is where this area has the concentration, has the real concentration there. So if you believe this is like behaves like a volume form of n-4, dimension n-4, then what you expect is the dimension of this set shouldn't be more than n-4, right? So that's essentially the proof you try to do here. Okay. So let me call this set to be the blow-up set of this. So that's where you may some curvature in the sequence may lose. Okay. So in order to do a compactness, so we have two things. So for any sequence, you have two things. In the limit, you have two things. So one thing is this limiting connection. Another thing is this subset where you have a concentration of curvatures. Okay. So of course, I said the Yang-Mills equation will be anti-self-dual property will be carried over to this limiting connection, and this outside S. But so what is the geometry of this S? So usually this is not it's a kind of difficulty question to understand the geometry of a singular set. Okay, when some objects develop singularities. So this is a time when the solutions in one status changes into another form. Okay. So that's my answer. So suppose, my answer, I give you two theorems. So let AI be any sequence in this modular space which converge to A infinity, still modular gauge transformations, and with blow-up locus. Okay, that's where the curvature concentrates again. So then this S, which I somehow, I apologize, I actually hide something here, because the S has to be counted with multiplicities, because there's how curvature, there's something measuring how curvature concentrates near S. So there's a density function involved, so which I hide. Okay, sorry about that. So anyway, so this S counted with the multiplicity, counted with density, is so that's why I put a dot here, which I can see. So it's actually integrable current. Actually, it's integrable subvariety cycle and which is K omega calibrated. So that means you can decompose into irreducible components SA, and MA is the multiplicity of that component, and each SA is calibrated cycles. It may have a singularity, just like holomorphic case, for example. Okay. So for example, in a holomorphic case, say if this omega, if M underlying manifold M is the Kähler manifold, and omega is this product of Kähler form with some normalizing constant, and we know, then I showed you before, these calibrated things are just holomorphic cycles. So I mean, as you see, holomorphic cycles may have singularities. Okay. But this having the things which have a singularity are rather not in the general position. So hopefully you can. I believe you don't. If you try to define some invariant I said before, eventually you don't need you want to push this away. Okay. So this second theorem, I talk about this limiting connection. So at A infinity is this limit, then I claim I proved there's a gauge transformation sigma such that sigma A infinity extends to be a smooth connection outside the subset such that the codimension is greater than 4. Okay, so dimension always counted as if before you know the structure of a set, it's always counted as a Hausdorff dimension. So in general, you don't expect SA infinity to be smooth, because for example, in the Keller case, what I mean in the Keller case, this first example I discussed, then the A infinity will give you a holomorphic sheaf on the M, and this sheaf in the high dimension may have singularities, which you cannot always remove them. So in high dimensions, you do expect some singularities. But for low dimensions, this was known to Karen Woodenbeck in the case of n equal to 4, which in that case you actually don't have this, because codimension more than the dimension now. Okay.
But do you actually have examples where the codimension set is 7?
Codimension example is yes, and at least let me pause this way. At least you can the one example you can construct is you take a cone over S6. Okay. So you think you are like on R7. So you try to construct a connection which is Yang-Mills solution of Yang-Mills equations, which are somehow invariant in a proper way along the radial directions. So then you reduce the problem on the S6. So in general, actually, I expect that this codimension is actually bigger to 6, because if you compute just the things I said a moment ago, if you compute the tangent cone, as also Jeff said, when you start singularity, always try to take a tangent maps. Like we start functions in the calculus, we always start first. I mean, at least we need to study derivatives. Okay. So in fact, if you check the tangent cone for this any omega anti-self-dual equations, and it always has singularity codimension 6. Okay, and the top dimension case and the dimension 6 case is in fact all this somehow this comes from a CP2, some holomorphic things from a CP2. So since you have such nice rigid structures, I expect that actually you can prove this, okay, but which I haven't done yet. So anyway, so in general, we have does have unremovable singularities, which I already said it a moment. So now I have two theorems. Let me say, so what is the computation you want before I give you some idea of a proof, which is getting short now. So in order to compactify, I need to assume M is compact, so that I have automatically has a bound on the L2 number curvature. Okay. So then I look at all the equivalence classes of a pair. So one is A is a connection, and which might be singular somewhere on a very small set. Okay. And it's omega anti-self-dual, and C is a cycle, which is calibrated. Okay, so I put them together. I require one more thing, namely, if you think, so this is area of A, it's like area of A, and this is area of C. So this all together should be fixed by topological quantity. So this is the case. This is the area if you don't have a C, right? As I said a moment ago, and this is to be kept. So this can be also interpreted as in fact for this so-called singular pairs here, which you can think is a singular version of a connection, omega anti-self-dual connection. So what you wrote this equation here is same as this second Chen character of this pair represents the same, represents C2. So here I assume C1 is 0. Okay. So this is rather like a homological condition for singular pair. So then let me define equivalence. So namely, the two pairs are equivalent if you C and equal to C prime, and then the A is gauge equivalent to A prime outside the singular set. Okay. Singular set. So then you can also talk about topology, which is basically specified before, already in the compactness theorem. Which so I say when it's compact, if Ci converges to a subcycle here, you may when in the limit you may get a bigger cycle, and the connection is converging after gauge transmission. So summarize what I did before from those two theorems. It basically says this is compact. Okay. See? So if you plot all the cycles, appropriate dimension, and appropriate homology class together with solutions of Yang-Mills equations, you will get compact things. So this n equal to 4, in case n equal to 4, is coincides with the 1, Uhlenbeck 1, used in the defined donut invariance. Well, in that case, you're adding just points in place of cycles. So in the last 5 minutes, I guess I have 5 more minutes. So let me give you some very sketched proof. So basically there are 4 steps in the proof. So first step, you try to prove a certain regularity theorem. So you want to prove S is actually rectifiable. So that's actually Jeff and Chica already defined before. So it's basically essentially it's a modular set of measure 0. It's just countable union of the Lipschitz image of Lipschitz maps, okay, from Euclidean space. And in particular, in this case, you can by a result of Federer, it's by a result from a geometric measure theory. You know this is actually equivalent to the TXS. The tangent space exists almost everywhere. So tangent space here means defined by GF before. You try to blow up things, scale. Okay. So, but I mean the tangent space now is really means this is a vector space in the ambient tangent space. So then you look at the area form. So I think this is area form for corresponding Yang-Mills now. So then this area will converge to an area of Yang-Mills connection, of limiting Yang-Mills connection, plus some density function and some delta function along S. So it's really the concentrated. So the delta S below this is forget it. So precisely this density can be defined as this. So it's a nice density function in this particular case, because by a careful study and using anti-self duality properties, you will be able to prove this integer value. It's important in the proof. So the step 3 you want to prove, because rectifiable has a lot more, is still too wide. So you want to prove in the third step, actually S in some sense has no boundary. So there are different ways to formulate it. Actually, I give 2 proofs in this step 2 case. So this is one possible proof. You try to prove that this is stationary with respect to it's stationary in the following sense. So sorry, there's a density forgot. Now X is any vector field with compact support. Okay. And the divergence S means the divergence along the S directions. Okay. So which is precise defined like this. Usually it contains two parts. One is divergence of S, and another part is mean curvature. Okay. So this actually says two things. One is has no boundary, and actually says it's a minimum in a appropriate sense. So then we come to this last step, so which is at least, though probably first few steps are very hard to understand in such a short time, but at least I hope you can understand this last lemma. So in the last step, in order to prove this is calibrated, the cycle, so I need to check the tangent space is calibrated by the appropriate linear form. So the linear form here is just restricting your differential form on to this ambient tangent space. So here you need to analyze bubbling property. So you try to get a nice bubbling, which keeps a lot of enough properties so that you can derive this property. So anyway, what we can do is by some analytical arguments, we can reduce. Sorry, I should say reduce this to a following simple lemma, which actually is now it's very easy. Actually, it's when I started this work, I went in a quite indirect way actually. So actually, beginning I worked in a special case. It turns out to be harder to prove than a general case when you realize this. So the proof is basically a few lines. Okay. So when I say if you're on the Euclidean space, look at the connection B, which is non-flat, okay, and such that the B vanishes along a lot of directions. The B is annihilated by all vector fields in the direction of S. So this is a vector space now. Okay. So then I say B being an anti-self dual, where forces this tangent space to be calibrated. Okay. So that's and particularly there says actually you might notice at the beginning I say I didn't assume omega to be non-vanishing somehow. So anyway, this will indicate the blows up only occur in the places where the omega is not vanishing. So once you have this, if you find the right B, you will be able to prove calibration. So thank you very much. Yes?
Do you think we can run the machine in the opposite direction, that we construct the calibrated submanifold?
I think so, yeah. It's like kind of asymptotic computation.
What was the question?
You can start with a minimum surface, try to do the inverse. And there are some technical problems, I should say. Formally, you can do just formally calculate in an asymptotic way. But maybe you want to ask whether each cycle can be a limit of that. It's you may need some generic conditions. Yeah. Yes.
In the case of anti-self-dual marginalized space, the classical case, what's his name? Parker and someone else have studied the geometry of the moduli space. They've given it a Riemannian metric. In your more general case, do you know anything about the geometry?
I don't know yet.
Are you thinking about it?
Not at the moment. No, I haven't got time to study. Yeah. And it could be there are some geometric structures on that. For that space. Yeah, but I don't know.
Which reduces to there.
Comment that there's another interesting example that worked out very implicitly on, for example, for turning on projective spaces. If you can look at this natural core form, the appropriate power of it. So this kind of anti-self-duality condition has been studied by Salomon and his students.
I see.
You can actually solve it as explicitly as any self-moving angle on the fourth sphere. You do in fact get simulation on subspaces.
Okay. Okay. Thank you. Yeah. Cool. Actually, I want to say, I want back to the question during the talk. I should say, I think I was asked whether or not I have an example of the omega anti-self-field connections on the dimension 7 with isolated singularity. And I don't have. I retreat from that. I don't have an explicit example yet. And this is, but you still can think about constructing a cone type solutions. And in that case, it's reduced to construct certain special Hermitian-Yang-Mills type connections on S6 with respect to this standard, with respect to these well-known almost complex structures. Because on the R7 you have a G2 structures, so then it will induce. You have the 3 form. It will induce the 2 form on S6, and then you can write down. It's almost complex. You can write down a Hermitian-Yang-Mills equation there, and I imagine there might be some nice solutions there, but I don't have explicit form. Yeah, thanks. Sorry about that. Yeah.
In the standard case, the way people get examples of anti-self-dual things is with twistor theory. You kind of lift things up to an associated algebraic bundle and do algebra. And I've often thought that would be a great way to get examples of singularity. So the question, and you can do that for harmonic maps too. So the question comes up, in your setting, is there some kind of associated algebraic bundle that you could lift this up, do some algebraic geometry constructions, and then produce examples of the kind of singularity you want?
It may be possible, but in some cases, I don't know if it's. For example, in the complex anti-self-field case, it might
You're not going to get everything.
It's actually interesting to see there's algebraic construction of that by twistors. Yeah.
In each of these examples of generalized self-dual, you would have hopefully moduli space. And I'm trying to work out the corresponding Cybert-Witten equation.
Not as I know. I think you made an attempt, right? So, not. I don't know. It's there. I mean, there's something discussed in this Donaldson and Thomas paper, but I mean, as you probably know, it's I don't know any abelian version of that.
But in the Sybert-Witten's original proof of the Sybert-Witten equation, they use kind of what they call duality, but it's kind of a sliding parameter that can take you from small to large parameters, and that sort of collapses things to the area of near singularities or whatever. It collapses things down. It's like puzzling.
Yeah.
So one wonders there must be some similar super.
You can discuss similar things there. It's like you crush, but you in that process you do need this kind of compactness theorem. That's actually maybe a possible application, which I think there must be a possible application like that. You for example take a product, you shrink one fact, and try to produce special cycles. It's like the academic limit process, nonlinear version of that.
Well, then this concludes the afternoon session.